Yep.
Okay.
Yeah. Go ahead, Mike.
Okay. Hi, everyone. Thanks for taking part in the and joining us for the latest machine learning network seminar. We're at the university. Well, we're in Sheffield, some of us, but it's being sort of represented by University of Sheffield. And today we've got Ollie Hamelijnck from the Alan Turing Institute down in London. He's going to be talking about air pollution and Gaussian processes and variational inference and various approaches to deal with these intractabilities. So he's a PhD student both there and at Warwick University. He's been helping me a lot with. He's the one that basically taught me variational inference, to be honest. So thanks for that, Ollie. I don't think there's that much more to say, really. I kind of feel like he'll talk for himself when he gets started. So I think I'll just stop talking and let you get started, Ollie. Thanks very much.
Awesome. Thanks, Mike, for the introduction, and thank you for having me here. Let me just start my slides. Okay, hopefully you guys can see my slides. Stop sharing. Yes, I think it's working. Okay, yes. So, as Mike said, I'm Ollie, I'm a PhD student, and today I'm going to be presenting some of the work that we've been doing at the Alan Turing Institute. So the talk is titled Multi-Resolution Multitask GPs with Gaussian Processes. And this is kind of, I'm going to be presenting some work that was accepted last year in Europe, and this is underpinning the kind of models that we're developing in the London Air Quality Project at the Alan Turing Institute. So just quickly, my collaborators on the paper were Wang, Theo, and Mark. There's too many people in the Air Quality Project to mention. So I've got some links here. So the first link is the link to the webpage, and this is the link to the paper that I just mentioned. So hopefully everyone can still hear me. Cool. So I'm just going to give a brief kind of overview of what I'm going to be talking about today. So I'm going to quickly kind of motivate why air pollution is interesting and how the air pollution project at Turing started and what it is, what the aims are, and what we're doing at the moment. And I'm going to give a very quick introduction to GPs and variational inference. I'm aware some of you probably know all this stuff like the back of your hand, but this is a public presentation, so just going to give a quick introduction to this. And that's going to introduce the kind of the framework that we're kind of dealing with, which is multi-resolution GPs, going to describe what this is and how this is kind of the starting point for the next two models that we actually proposed in Europe last year. So these are multitask models. So we've got two different variants. One is multi-resolution GPRN and one is the multi-resolution DeepGP. The acronyms don't matter now, we'll get into those later. And then I'll just quickly go through some experiments to kind of show that these methods work and show you some of the outcomes that we're having from the London Air Quality Project at Turing. And then just quickly go through some conclusions and some future directions. Cool. So, just to briefly motivate why this is an interesting problem, why air pollution is an interesting problem. So I'm just quickly going to define what we mean by air pollution. So typically, there's lots of pollutants that can be kind of generalized by the term, well, the umbrella term air pollution. So some of the ones I plotted here in the time series is we've got NO2 and ozone, where we're interested in modeling the concentration of these. And then there's PM10 and PM25, where we're interested in modeling the amount of particles that are in the air. Now, just a few facts on air pollution, or on some of these pollutants. So NO2 is said to be produced by 50% of it. NO2 is said to be coming from traffic. This is in London. And NO2 inflames the lungs, and it can cause shortness of breath and further kind of chronic problems. And PM10 has a kind of similar deal, that the particles get stuck in your airways and they can go to the bottom of your lungs. And this has been linked to early deaths and worsening of heart and lung diseases. So these are important things to understand when they're high and when the levels are unhealthy levels. So, yes. So air pollution as most of you probably know, is a major problem in many cities and countries around the world. So in the UK alone, 40,000 there are 40,000 early deaths a year, an estimated 40,000 early deaths a year. And globally, around 80% of people live in urban areas that where air pollution is at unhealthy levels. So this would kind of explain why in the past few years, London has made air pollution and air quality a kind of top priority and a priority. And there's been a number of new policies and actions to try and reduce the air pollution levels. And some of these have been quite successful, but at the moment, there's kind of no way to kind of assess these changes or assess these policies. And one of the main reasons for that is because the models that they're using, or the existing models that they have at the City Hall, are mechanistic models. So they're static, expensive to run, and they provide no uncertainty quantification. And what I mean by static here is that they're actually using data from 3 years ago. That's because it's so expensive to run. So they run it once every 3 years, and then they just slightly calibrate this model on a yearly basis, just to kind of give more up-to-date predictions, but it's still using out-of-date information. So that's where our project comes in, where the London Air Quality Project comes in. So at the Ellen Turing Institute, we are collaborating with Greater London Authority, so this is the City Hall of London. And we want to understand and model air pollution across London, as I said. So the first kind of aim, I guess, is that we want to bring data from a wide range of networks and sensors into a single place for analysis. So this includes air pollution data, perhaps from the London Air Quality Network, from satellite observations. It also includes things like traffic data, weather data, land use data, and a whole host of other data sets. And one subpoint of this is that these sensor networks are from a range of qualities of sensors. So we have very cheap sensors of air quality, we have very expensive sensors of air quality, and we want to be able to utilize all of this information as best as we can. And using all of this data, we want to be able to provide 48-hour spatial temporal forecasts of air pollution across London. So this means that every day we want to be training our models overnight using the most recent data that we have and providing these 48-hour forecasts for the next 2 days and repeat every day, such that we can give this kind of real-time dynamic forecast of air pollution. And then the main idea is that we want to release these maps in the form of an API, or people can come to the website and see the maps, and then people could do with that as they wish. But internally, we're also looking at things you can do with these maps, such as providing optimal low pollution running routes. I won't focus on that anymore in this talk, but I'm just going to say it here. Okay, cool. So I've introduced the aims of the project. I just want to give you kind of a taste of what the data that we actually have is. So this is, on the left-hand side, some air pollution data. So this is from the London Air Quality Network, which is run by King's College and GLA. And this is PM10 for site HV1 in, I think it was last January, or this January to March. So data is noisy, as you can see from the left-hand side. It's miscalibrated. So this line is representing 0, and we have values that are below 0, which shouldn't make sense. We have lots of missing observations. So this is just small. This is only for 3 months, but if I had to plot it the whole year, there'd be loads of these gaps where we have missing observations. And this is just in the London Air Quality Network. In the cheaper sensors, it turns out you can't actually trust the raw values that are coming from the sensors. So what this means is that if you have 2 cheap sensors next to each other, and one of them says high air pollution and one says low air pollution, you can trust that relatively there's high air pollution at the high air pollution sensor. But you can't actually trust the value of air pollution that's coming from these, which is, of course, a big problem. Some additional data sources that we have. Let's hope that I can play this video now. Okay. So what I've plotted here is observations or data from a ECMWF satellite model. So this is actually a massive air pollution model that's defined over the whole of EU, and it provides forecasts on these 5 by 7, depending on where you are in that region, kilometer grid cells. And each cell is representing the average value of, in this case, NO2 for that cell. So we want to be able to utilize data coming from these models and these satellite observations as well. And then we want, and here's just a kind of a little example of some additional data sources that we have. So we have data sources on the land use in London, so where all the roads are, where all the parks are, where all the rivers are, where all the buildings are, what the types of buildings actually are, the businesses, the homes. And we have stuff about the road layout, such as the type of road, so if it's an A road, a B road, or a C road. And we have data from TfL, from scoop sensors. So these provide information on traffic data, and they provide in real time. So this bottom middle one is actually a time series from one of these scoop sensors. And so the biggest, I guess, one of the challenges of this project is how do we combine all of these data sets that I just presented to you together. And at the end of the presentation, I have a small video which shows one of the outcomes of the project, which is a quick, I think it's a 24-hour forecast from some of the models using all of these data sets. Okay, cool. So I've introduced the project and the data sets that we're dealing with and some of the problems that we have in the data sets. And now I'm going to start digging into some of the models that we're using to kind of achieve the goals that we want to achieve. And our kind of model of choice to do this is a Gaussian process. The reason for this is that they can naturally handle missing data, they can easily be applied to the spatial temporal setting, and they provide uncertainty over predictions, which is very important for when we're doing policy analysis. So I'm just going to quickly cover some of the basics of GPs. Some will be very formal, just going to be kind of a quick summary, and some of the how inference is done in them. So quickly going to go through variational inference. Hopefully not too quickly, and hopefully not too slowly. Okay, cool. So the kind of what the situation that we're in is we have some observations XY, some input output pairs, and we have that plotted on the left hand side, and we want to fit some function or some model to the data. But which function should we choose? I could pick this one, it seems to do quite well. I could also pick this one, which is also seemingly pretty good. I could probably pick any of these functions and I'd be pretty happy. But instead of just picking one, what I can do is I can define a distribution or a prior over functions, which is a Gaussian process. And then I could get uncertainty in my model fits because I'm defining a distribution over all of these functions. So that's kind of the pictorial understanding, I guess, over GP, just distributions over functions. And if I play this animation, you can see some of the samples from this GP. But slightly more formally, a GP is defined fully by the mean and kernel functions. Now I haven't put the mean function here because this can be absorbed directly in the kernel, so we assume 0 mean GP. And we define a prior over F. And then we can just use the machinery of Bayes and observe some data and learn a posteriori of F. Now inside the GP, there's a bunch of parameters inside the kernel and inside the likelihood. So I've just been lazy and used the same theta to note both of these, the likelihood and the prior. And we can just optimize these with respect to the log marginal likelihood using type 2 ML. Cool, so that was a kind of whistle-stop tour through GPs. And that was kind of the naive GP, I guess. And there's a bunch of extensions to GPs. So as I said, extending to the spatial temporal setting is simple. We just have to define our input space to be space-time, and then just define a suitable kernel. for a bunch of different space-time kernels. You can see our recent paper with Hongui Wang in ICML. And one kind of downside, I guess, or the biggest downside of GPs is the qubit complexity that comes from inverting this kernel matrix, which is n by n, so it's an n-cube operation. So what is typically done, or what can be done nowadays, is to use a sparse GP, which essentially just introduces pseudo observations, and these act as a kind of low rank approximation to this kernel, and then we get down to O n cubed, or plus n squared. I've tried to kind of hide these details from the rest of the presentation because I guess nowadays they're kind of standard. But there are some references at the bottom, and you can go to the main paper and we expand on all of these details on how they relate to the models that I'm going to be presenting to you. Cool. So the last thing I just need to quickly introduce before going into models is what is variational inference. So instead of finding the true posterior in closed form or through sampling, what we can do is just pick a approximate posterior, a Q of f, with a nice family, that is just a Gaussian, something that's easy to use, and then we just try and make that guy as close as possible to the true posterior. So we try to minimize some divergence, or the KL divergence, between these two distributions. Unfortunately, in most cases, we can't actually directly optimize this guy, but it turns out that if we maximize the elbow instead, this is equivalent to minimizing the KL between these two guys. So we work with the elbow instead. And the elbow is typically decomposed into these two terms. So you get this better log likelihood term and this KL term. This KL term is usually pretty easy to write down in closed form because it's usually just between two Gaussians, because it's between the approximate posterior and the prior. And this better log likelihood term is where a bit of the algebra and a bit of the tricks have to come in. So this is where we've strived to try and get closed form as better log likelihoods, but when that's not possible, you have to resort to some kind of black box method, so either Monte Carlo or some kind of quadrature to evaluate this. Cool. Hopefully that wasn't too fast. But now, so I've introduced GPs and VI very quickly. So now I'm going to introduce the framework, or the idea underpinning the two models we proposed in Europe, and the models that we use in the Alan Turing Institute. And these are what we call multi-resolution GPs. So the main idea of them is to allow GPs to use observations defined over some area, so some area observations, or some data defined at the average of some area. So on the left-hand side, what we have here is the satellite. I have plotted the satellite observations, just 4 satellite observations, and this is the river Thames, so this is in London. And I'm just going to double check that I'm still presenting properly. Okay, cool. Sorry about that.
Yep, this looks fine. Yep.
Cool. So yes, so we have some satellite observations, or some area observations, and we're going to denote this area that the observation is defined over by this mathcat A. And then we can just define our observation model as integrating the latent GP over this whole area, getting the average, so normalized by the volume, and then adding on some noise. Now, typically, this integral is not generally tractable, especially with some interesting kernels, or when f is not Gaussian, or in lots of situations this is not tractable. So we discretize the integral, and we do that by introducing discretization points. And here I just overload the mathcal A to denote how many points we have. So a bit more kind of formally, I guess. In general, we don't just have one observation. We're going to have D different data sets. Each could be a multi-resolution data set. So X is now going to be a list that holds each of these data sets, and each one of the elements inside this list is going to be in N by AD by D. So I'm explicitly writing X as being a discretized version of the integral. And then our likelihood for a model or joint or posterior simply becomes the equation I put at the bottom. So we just have P of y given F, and we have the prior in F. And now we've got these data sets. So when all of these observations are independent, so when the noise of these observations are independent, we can write this as a product likelihood. So we get the product over all of these data sets, and then we just have an individual likelihood term for each of these data sets. The reason I wrote an approximation here is that the noise of these data sets is not always independent. So for instance, in London, there's a sensor network called diffusion tubes and the London Air Quality Network. And the diffusion tubes are defined as the monthly averages of air pollution at given locations. But before we get the data, what they actually do is they run a simple kind of OLS thing to calibrate the diffusion tubes to the London Air Quality Network data. So already they're kind of tying in the noise of the London Air Quality data into the diffusion tube values. So there, this product assumption would be violated. So that's why I just wrote an approximation sign here. I'll touch on this a little bit later on, but we talk about this more in the main paper. Cool. So the nice thing about these models is that when we have the product likelihood, the expected log likelihood term is available in closed form, so we can easily use variational inference. I won't go into this, it's just to show that we can do it. This slide. And here I've just put some related literature on multi-resolution GPs that was already out there. So in GPs literature, this is kind of more known as aggregated GPs, I guess. So the second two citations are actually concurrent submissions to NeurIPS last year. And in spatial statistics, this is known as the change of support problem. And it also goes under the name of, or similar to stuff like line observations or integral observations. The reason we call it multi-res is because when working with the Greater London Authority, this is how they call the different type of data sets. So they have low resolution data and they have high resolution data. So we've adopted that name. Okay, awesome. So before going into the models, I'm just going to quickly define what multitask is, and then we can jump right in. So what is multitask? What does this mean? So instead of having just one output, so we have y and r and 1, we now have p different outputs, so p different tasks. And I can reuse the picture of the air pollution because each of these pollutants, so NO2, O3, PM10, PM25, we can treat them as different tasks. So in this case, y would be in Rn4. So we have a multivariate output, and we want to somehow learn the covariance between these outputs such that we can make better predictions when predicting just one of these outputs, or when predicting all of them. So just going to present or quickly rush through two existing multitask models in GP literature. There's a host of different ones, but these are the ones that we extended in the paper. So these are the ones we're going to introduce. And the common idea in both of them is that we want to capture the covariance between the different tasks, so between the NO2 and the PM10, by introducing a common set of latent functions. So on the left-hand side, I have this picture here. So these F1 to FQs are the common latent functions that are shared within all tasks. And then we're going to, because they're shared, there's going to be some shared covariance between the tasks now. So in the first model, the linear model of co-realization, you have these Q latent functions, and then we're going to tie the latent functions to the specific task by taking a linear combination of the latent functions. And these W here are just task-specific weights, which just weight the latent functions in a task-specific manner. The GPRN extends this by allowing the weights that are used in this mixing to also be driven by GP. So this allows you to have a covariance matrix, like covariance between the tasks to change in input space, and it also gives you some kind of non-stationarity. But given a GPRN, we could just let the W not be a GP anymore and just let it be a hyperparameter, and then reduce back to the MC. So yes. So the Gaussian process regression, I didn't add the citation here, but that is by Andrew Gordon Wilson. I probably should have added that. Cool. So now I'm going to introduce the first model that we proposed, and it's called a multi-resolution Gaussian process regression network. So as the name kind of implies, we're going to have a GPRN prior. So we're going to have Q latent functions, then we're going to have PQ extra GPs, which are going to act as the weights. But now each task is going to be observed through multiple observation processes. So for each task, I'm going to have D data sets at D different resolutions, which is observing that task. So this is the GPRN structure. So we have the product over the tasks, and we've got the Q latent functions, the QF latent functions, and then we've got the GP weightings. And this is the multi-resolution structure, the multi-resolution observation structure, as I already presented. I wrote it as an core here, but in general, well, this is discretized as before. And this little weight here, if you might have noticed, this little phi is actually a composite likelihood. So the likelihood that we propose is actually a composite likelihood. And the reason we do this is that we're trying to tackle this product likelihood assumption for the cases such as the diffusion tubes and the air quality network situation I described earlier. And I'm not going to go into more details on this, but you can see the main paper for extra detail, for more details on this. So yeah, so this is the likelihood that we are using. So it allows us to have multitask observations and allows us to have multi-resolution observations. So this sounds good. So for inference, we use variational inference. I don't go into many of the details here because it would be a bit laborious. But the main idea is that we follow Bonilla, and in these two papers that are cited here, we introduce a mixture of Gaussians. So we have these Q latent functions. We introduce an approximate posterior for each of the Q latent functions and each of the PQ weighting functions. And we augment each latent function with inducing points, such that we get computational speedups. And we can derive closed form as better local likelihood terms and predictions for the mean and variance. So inference in this model is not too bad, computationally speaking, not generally speaking. So, just as a small recap of those few slides, I quickly kind of presented a model called MRGPRN, or the multi-resolution Gaussian process regression network, which is an extension to the GPRN, to the multi-resolution setting. I'm now going to present an alternative model that we proposed. And the reason we have two is that this one focuses on the calibration problem where you cannot trust the raw values of the data sets that you have. So between these D data sets, you can't trust the raw values, so you don't just want to use it naively. And we're interested, and in the second model that I'm proposing, it can also maintain high resolution structure. So when you're predicting in regions where you only have low resolution observations, you can still maintain high resolution structure. So this is some kind of super resolution, or some kind of super resolution model. Cool. So the main idea about the model, so the main idea is that we want to calibrate the sensors that we can't trust the raw values of to a data set that we do trust the raw values of. So in our case, this would be the London Air Quality Network. This is the research quality observation, so we trust those values. And we want to calibrate the data to it. So what we do is we, as this pictorial diagram is trying to show, we have some data. So in this case, it's satellite data. And we're going to learn a mapping from the satellite data, or the function of the satellite data, to the LAQN data. Now, if this mapping is driven by a GP, and both of these guys are driven by GPs, we're actually defining a deep GP where we are modeling multi-resolution observations at each layer. So this is kind of this is quite a nice GP because the deep GP now has meaning at each layer, just kind of naturally defined, which is very nice. And it allows us to calibrate between data sets. And by having this deep structure, and by calibrating between data sets, we are allowing predictions to maintain the high resolution structure at the top layer. But we can still predict at the lower resolution. We can just predict each layer and just take the predictions out. So slightly formalizing this slide a little bit, the previous slide a little bit. We now have the plate diagram for a single task. So in the previous diagram, I only had 2 data sets, but in general, we have D of them. So we're going to have D different Ys, so D different data sets. And because we're doing some kind of calibration, we need to choose a high resolution observation process to calibrate towards. So typically, in our examples, this has been the London Air Quality Network. So this is this Y1P. So we just pick that guy to be the target resolution. And now we're going to calibrate all other observation processes to this data set. So what this means is that we're actually going to get D independent models that are kind of experts in the area where the low resolution data is defined. So now we just need a way to kind of combine each of these D data sets together to give a unified prediction at the Y1P level. And the way we do that is we combine them using a mixture of vectors approach. So because each of the D GPs I just defined were independent, we can just add them together and we get a weighted combination of these guys. And this would be a mixture of vectors approach. Now this is also nice because this allows us to use data that is non-overlapping. So let's say we had one low resolution structure defined, or low resolution observations defined in Camden and one defined in Islington. These are disjoint space. We can still use these guys as long as they overlap with the target resolution or the target observation process. So just a few details on how we're defining the GPs inside here. So each of the DGPs are the guys that take the low resolution structure and calibrate it to the high resolution structure is a DGP defined as this. So in this case, this FDP would be the GP over the satellite data. And then we augment the input space with X such that this calibration function can vary across input space. So we got a very flexible calibration function. And this FDDP2 would be the GP that's targeting the high resolution structure, so the LAQN network. And then we're combining each of these experts, so the experts that are defining the calibration from the low resolution to the high resolution target. And because they're independent, we can just get a linear combination of these guys. And that's defined as this. So what I've been talking about at the moment has been a single task, but this can be naturally extended to the multitask setting by introducing all the tasks. And as I said, we have D data sets per task. So we're going to essentially do the same idea as we did within the single task and just apply it to the P tasks. So we're going to choose a target task, and then we're going to learn a mapping from all the other tasks to that guy. And so what we're actually doing is defining a tree-shaped mixture of experts. So this is the target task at the target resolution, and each of these guys are the mixture of experts of all of the other tasks. So you combine all of the task-specific data sets inside here, and then we combine them at this level to give a unified prediction at this target task and resolution. So yeah, inference in this model flows close. We use variation inference again, and we introduce inducer points for every latent function that we have. And so inference closely follows the double stochastic framework of Hamelijnck. So this is the approximate posterior, which I won't go into. But basically, the idea is that the KL term at the bottom is easy to compute because it's just a bunch of KLs being Gaussians. But to evaluate the expected log likelihood, we need to sample from the base GPs, so the low resolution structure, the low resolution GPs, and then propagate those samples up the tree. In practice, we found this is not hindering the project, we can still run this overnight and give 40-hour predictions. So this is fine. Cool. So that was hopefully not a too quick tour through the two models that we proposed. But these models are at the heart of the project, at the heart of the models that we're using in the air pollution project. So I just want to show you some of the results that we're getting from the project and some of the results that we presented in the paper, in the Neuros paper last year. So in this first experiment, in this first tour experiment, I wanted to demonstrate the idea of calibrating between the low resolution data to the high resolution data. So we've got 3 different data sets in it, or different observation processes. So the high resolution ones are given by crosses. So this is these lines. And then we've got 2 different low resolution data sets given by the lines. There's one here, and then it splits that one here. And so this is the training period, where we have both the black crosses and we have both the black lines. And then in the testing period, which is outside of this box, we only have the black lines. So in this training period, we can see that all the models, so MR-DGP, MR-GPRN, and VBAG, which is essentially the multi-resolution GP that I presented halfway through the slide, can all fit to the high resolution data as expected. But as we go away from the training period, which is where we have the high resolution data, VBAG and MR-GPRN actually start to now follow the low resolution data. So they haven't learned this mapping between the low resolution data and the high resolution data, so they just fall back on it. Whereas MR-DGP, because it's actually learned this calibration function between them, can still predict at the high resolution observations. And this idea that MR-DGP can do this is the same in this next experiment, which is a real-world experiment, which provides spatiotemporal predictions across London. So in this experiment, we were modeling NO2 from the LAQN network, and we're using satellite observations from the ECMWF air quality model that I showed you the animation of at the beginning. So these are denoted by, on the left-hand side, we've got these pictorial things for, this guy is the ground sensors, and this is the satellite. So in the top row, we have both the ground and the LAQ and the satellite, and in the second row, we only have the satellite observations. We've also included some additional features in these data. So we've got stuff about where the river is, about where the roads are, about where all the parks are. And that's why we've got some nice structure in these maps. So yeah, as I said, in the top row, we have both satellite observations and we have LAQN observations. And all models are able to capture some form of high resolution structure. As we can see the rivers and we see some of the road structure. As we predict, I think this is 12 hours ahead, but we only have satellite observations, only the MR-DGP is able to retain this structure nicely. And this is because it's able to learn the calibration from the satellite to the LAQN and apply that in the prediction region. So this not only makes pretty maps, it also, this table of results is showing the results when in the prediction period, which is a 48-hour window. And the DGP is able to outperform all of the other models because it's able to learn this calibration. So in this experiment, we did a multitask experiment where we had different PM10 resolutions. These were synthetically made. We just averaged the PM10 observations that we had and did different sizes of resolution. This is just to show that we can do multitask essentially, but we don't have any pictures for this in this slide, so I'm going to refer to the paper for more details on this experiment. And I want to play this video first. So this is the video that I mentioned at the beginning, which is an outcome of the London Air Quality Project. So I'll let it play a few times, and then I'll describe what it's kind of showing. Hopefully, with internet, everyone can see the frame rate is not too bad for everyone. But what this map is showing is we've combined all of the data sets that I described at the beginning. So we have traffic data, we have data on where the roads are, where the buildings are, where all the parks are, where the river is. I'm using the LAQN data, I'm using satellite data. And this is just a 12-hour, I think it's only 12-hour forecast from these models. So you can see we get some nice daily fluctuations throughout the day. And these are the sorts of maps that we're going to be producing every day for the next 48 hours. So you really do give a kind of real-time feel and real-time model of air pollution in London. What I haven't plotted here is uncertainty. I could have had another map showing how the uncertainty changes throughout the day, but I haven't included that here. Awesome. So that's the two models I wanted to present and some of the experiments and outcomes of the project that we have and have already presented. So I just want to kind of summarize what I've presented today. So I've introduced a non-parametric framework that can handle both multi-resolution and multitask observations, and applied these in the spatial temporal settings. These models offer evidence integration, and it can naturally handle calibration between the data sets, and naturally handles multi-fidelity modeling. I didn't highlight that too much in the paper, but in the talk, sorry, but in the paper, every likelihood for the data, each data observation process has its own noise, so we can handle different noise terms for each data set. We proposed two models, a shallow MR-GPRN and a deep MR-DPGP, and kind of explored some of the different properties of these guys. And when possible, we've derived closed form expressions for the expected log likelihood terms. So in the GPRM, we've derived closed form expressions. And as I've said, I was going to hide the details of this, but we included inducer points for latent functions for scalability. Now, there's lots of future directions that we can go with this, with the project, and we are going with the project. So just kind of a quick summary of some of the directions that we're looking at and we want to look at and could be explored with this project. So as you saw at the beginning, the air pollution data was pretty noisy, and there's a lot of outliers. So what we could do is try to improve this model specification. So we're using Gaussian likelihood, which is probably specified, using recent advances as GBI. So this is a paper by Jeremiah. Yeah. So in the paper, what we used was we used separable kernels. So I think we use a mixture of like RBF and Matone kernels, which is kind of standard in GPs. But there's no reason why we couldn't choose a more expressive kernel, maybe a non-stationary and a non-separable kernel. So what we're looking into is, can we use the kernels like Hungary Wang, who's the third author on this paper, that I presented today? Can we bring those into the models, and what do we gain? And can we get more expressive predictions by using these? So instead of using a mixture of experts approach in the deep GP, we could explore this line of work by Dieselroth and the references therein on distributed Gaussian processes, and where they combine them using a product of experts approach. Because this might link more nicely into the literature that's already around. Oh, sorry. And is it possible to develop, not to avoid this domain discretization? So can we avoid having to discretize this integral in situations where we have complex kernels, or the area that we're actually integrating over is not in nice shape? So just included some citations here. And that is the presentation. So I have some references here. I don't know if these slides are actually shared, so I don't know how useful these are, but if I just flick through them now, I guess if any pop out. So that's the presentation. Thank you very much for listening.
Cool. Thanks very much, Ollie. Yeah, thanks everyone for taking part. Feel free to ask questions and things. I've been asking, and I've got a lot more questions to ask of it another time, to be honest. So, but it would be probably best if other people want to ask any questions of his talk. If you've got any comments or suggestions, even of what you could apply it to next. I'll be also, I guess, Ollie, would be interesting as well, like other domains where this could be applied. I feel like it's quite a general problem. I'm kind of I'll talk to you about another time, but I'm interested in some ecological data sets, which I feel like have a similar sort of flavor to this, where you've got like quite a lot of side information and quite noisy sampling and things, like transects and stuff are like by definition like an integral, aren't they? So it'll be interesting to see where that applies. So I can have a look at the questions that, like, to be honest, 3 of them are me. I just kind of couldn't resist asking them.
No worries.
But actually, the first question, which I guess is not by me anyway, which is good, is questions about the link to the, obviously what everyone's talking about these days. It's quite nice to have your talk. For a few minutes, we weren't thinking about coronavirus, but someone had to spoil it and mention it. So how's it, have you got any knowledge or any insights from your work on its connection with like exacerbating coronavirus? I feel like that's probably outside your expert area maybe, but I don't know whether you've got any thoughts on this, or could you even include hospital data maybe on a side note as a piece of side information for your work? But
yeah, so I don't want to comment too much about the actual effects of air pollution on coronavirus. I'm going to leave that to experts in the field, so I guess medical people. But another way to kind of look at this question is there anything that the local governments can do to try and analyze what's going on and see if the policies that are actually being introduced are actually working? This is to do with coronavirus. So not really to the air pollution, but to the coronavirus. And the reason I say this is that a lot of the work that we've done in the London Air Quality Project has been analyzing data of people's movements. So this is to do with the traffic data. We've got the running routes, so data on kind of the movement of Londoners. And so a lot of this stuff has now been kind of repurposed in a way in the London Business Project. So this is another project at Turing, which is headed by Theodore Munas, who is the second, who's my supervisor. And what they're doing is they're trying to repurpose some of the tools and algorithms that we've already developed in the London Air Quality Project and use them to actually analyze how people are moving in London. So is the policies that has been set, are they actually being stuck to? Are they working, essentially? So let me Google, because it probably shouldn't Google stuff like.
So is that like using the air pollution as a proxy for how people move? Is that what you mean? Or do you mean like how that relates to where people are going to be exposed to the pollution?
Yes, it's not explicitly related to the pollution. It's more about the data sets that are.
Oh, I see. Okay, right. You're using the
like
same method. Gotcha. I'm sorry, I understand now. Yeah.
So using the traffic data to understand as a proxy to where people are moving around London, and if people are sticking to the 2-meter rule and that sort of thing. So this is the project webpage. So if you want to know more, you can go on.
Cool. Okay. Yeah. Thanks for that. That's interesting. Of course, there's already another example of like where those methods can be used. Can I ask a sort of vaguely technical question? I think you probably said it already, and I think I maybe kind of knew this at one point, but I've sort of forgotten. So I'm going to cheekily ask one of my own questions. It's around the structure of the the variational approximation to the posterior in your GPRN model. Where are the dependencies or independencies? What do you assume is correlated, as it were, and what's which of the Gaussian processes have like correlations between the functions, as it were, and which ones are assumed like to model as independent in the posterior? So
if I understand the question, you're kind of asking in the posterior, what are the kind of mean field assumptions? Or
yes, exactly. Yeah. Bigger. Yeah.
So for most of the experiments we actually just assumed a mean field approximation. We derived the approximate posterior to be a mixture of Gaussians, but actually in most of the experiments we just used mean field approximation, mainly because it was good enough for the predictions that we needed, and for the focus of the experiments, it was more on the prediction, not on the quality of the approximate posterior.
Uncertainty. Okay.
And we found
Yeah.
that has been fine for the experiments that we've been doing.
Right. Okay. Yeah. Yeah. Do you think it's just that? Do you think the uncertainty is well quantified, or do you think actually the posterior is fairly like independent anyway, so it doesn't matter which side of the of that coin do you think you are?
Yeah, so this is, I would say, it's kind of been good. Like the surgical quantification has been good enough for what we've been using it for, but it's probably not amazing. As it's kind of, the problem is that if you want to add more, if you want to capture the correlation between all the latent functions, that's actually quite a hard problem to do. Like, you just have a massive tensor approximate posterior, so then you have loads of parameters, or should I be using these kind of HMC approaches, so this kind of variational HMC for variation sparse GPs, where you can just have an arbitrary approximate posterior, should I be using this? But then you have to sample.
Tell me about it.
So one of the focuses on the paper is to, on the project, is to do these things every day. So we do have some kind of computational limits that we have to adhere to.
Yeah. That makes me sorry. I should really read other people's questions. There aren't any other questions at the moment, I think. So I can just going to ask you more questions that lead on from that. So one of the things that's interesting from that is you every day you're giving a new prediction, right, for the city. So how do you might have already mentioned this in the talk. I was too busy thinking during your talk at the same time of other things. But how do you deal with the streaming aspect? Do you just rerun the whole model, or do you somehow have a clever way of just updating it every day?
No, at the moment we are just rerunning every day.
Okay.
So we just take the last week or 2 weeks, or depending on what model you want to use, and we just train every day.
Do you learn for the hyperparameters and stuff? Do you run it like for a longer period, like for more data, like you know what I mean, like with more computation, as it were, resourced occasionally to estimate the hyperparameters, or do you find a week is enough time to like give you good estimates on those, like things like length scales and stuff?
Yeah, we found that a week is usually suitable enough, and we also, because we're bringing a lot of data in, so we're taking data from the European satellite model, so this is defined over the EU, and a lot of that has information in there as well. So we kind of get away with some of the problems of that because we're using so many different data sets.
Cool. Okay. Yeah. Really quickly on the there's so many questions on things like the satellite data and stuff. I sort of feel like there might be things like more complicated, like non-linearities in the actual like function that goes from the actual pollution to the number they give you. So there might be a ceiling effect, or I don't know, like some other horrible non-linearity, or does it have an offset, or other unpleasantnesses in the in that. Have you thought about how you deal with that, or is that just not really worth worrying about? Or supposing there's a ceiling effect, or supposing there's an offset in one of your in like the measurement given you by the satellite.
So you're kind of asking if this, what do you mean by ceiling effect?
Okay, supposing one of your cheap sensors only goes up to 50 micrograms per cubic meter or something, then then it sort of flattens off or something, because there's like a non-linear sort of link function happening there in terms of the actual observation.
Mm-hmm.
I don't know whether you've worried about that. It's just I'm giving you more problems to worry about. Sorry.
No, so we haven't worried about that problem exactly, but the problem I think that you're implying with the offsetting, so where the data you can't really trust the raw value of.
Yeah, it's
just
like
something that we've worried about, and that's kind of the motivation of the MR DGP model, where we basically try to calibrate to a data set where we do know the real value. So kind of similar to some of the stuff that you've been talking to me about.
True, that's fair.
And so we're letting this be driven by a GP, and this calibration function can then change for the input space. So we can have quite flexible calibrations.
Right, yeah, of course.
But we've not really thought about the case where a sensor reaches a ceiling and dies.
Right. Okay. Yeah. No, that's fine. I think you already answered the question actually with the deep GP. Yeah, that's true. Has anyone else any questions while I've been wittering?
Can I go ahead and ask one, Mike?
Yeah, sure, definitely. Yeah.
So I'm not from this field at all about using GPs and so on. But it just got me thinking. There was a slide where you showed some latent variables generating, was it multitask GP or something?
Yeah.
Where you had various latent variables generating GPs which were correlated and so on. And so, no, my question was more, yeah, that one.
Yeah.
It was about whether you could actually generate some kind of a dynamical model out of it. So could you, for example, use these GPs to come up with some latent dynamics examples, which actually are the generative process which generates this data? That was the kind of.
Yeah, I don't, my expertise is not in this field, so I'm not going to be able to answer this question very well. But maybe you want to look more on Maritha's work on latent force models, or maybe using GPs as the driving terms inside of these STU models. I'm afraid that's not the best answer. But...
No, cool, thanks. So whose work did you mention?
Mike Maritha. Google latent.
Oh, I see. After Maurizio's paper, right?
I think
he's on the court. He's one of the participants.
He's at Sheffield. Yeah.
He's keeping very quiet, but he's one of the attendees.
Yeah, he is around.
But if you go through his kind of published work, you'll see a lot of related stuff to multitask models and latent force models. So that'll probably be a better answer.
Also, maybe if you want to learn more and on that particular topic, maybe Maurizio's talks from the Gaussian Process Summer School on YouTube would be maybe a good place to go as well. Just, I thought.
Oh gosh, I'm downloading something now.
Has anyone else got any questions from the audience?
There seems to be.
Is there another one?
There's one by Juan Jose.
One. Yep, cool. Okay. I guess we can all read it. I guess I'll read it aloud. Or actually, I should get Juan to read it.
Let me invite him on screen. Close your screen sharing, Ollie. Yeah, that will allow us to invite.
Yeah, how do I do that?
Yep. If you stop sharing, let me close it for you. Yeah.
Okay. Is it working now?
I'm not sure if he's managed to come on. Probably not. No, I don't think he's managed to come on. Okay, so maybe Mike or can just ask the question. Maybe I can just read out. So it says, thanks for the talk. I was wondering if the inducing point set is defined as a unique set shared over all latent functions, or do you define a specific set for each different latent function? If the latter, do they share the same size M?
So there's two different models, so I guess I'll answer two different questions. In the code for the first model, so the MRGPRN, we actually use the same inducing point locations, but the values of the M and the S that you learn can all vary depending on input space. And for the MRDPGP, they can all be in different input locations. They all share the same size M. The reason for that was mainly a computational thing. It was a lot easier to code because it could treat it as a tensor, and then TensorFlow just can deal with it. You don't have to worry about lists. But there's no reason why you can't have different number of inducing points for each GP. There's no limitation theoretically for that, at least not I'm aware of.
Cool. Yeah, that makes sense. Yeah, I'm just to butt in there with a sort of vaguely related model at the moment. The motorbike taxis in the Kampala project are really sort of a similar problem in the calibration, and they get corrupted really quickly, like they get degraded really quickly. Whereas the static stations on top of posts last for months. So we've actually gone with a shorter length scale and more inducing points for the mobile ones. So there's actually it becomes worth the extra hassle of So yeah. Cool. Thanks for that. That's a really good point. That's a really good question because it's something I've been worrying about a little bit myself. Cool. I'm not going to ask any more of my questions now because I feel like I can bug you over email at any time. So, yeah, it's the last chance for anyone to ask any questions. I think. Does anyone else have any thoughts, or feel free to put any comments as well as if you want to in the chat, or any other suggestions on what to apply it to. I might have to talk to you about applying it to Bumblebee bee walk data as well. It'd be kind of cool. Yeah, but I think that's probably it. Aditya, do you want to sort of finish?
That's it, and I think we're this is our last talk before the summer break, and then we meet again after sometime in September, I guess, for the machine learning seminar series.
Cool. Thanks very much. Hey, thanks Ollie again for taking part, and thanks everyone for coming on and taking part. Brilliant. Cool. Take care, everyone. Yeah.
Take care.
See you after the break.
Thanks,